Yeah. Okay. Thanks to the organizers for all the hard works and giving me an opportunity to talk about my work. So today I'm going to talk about some of my recent work with various collaborators here. In the first half of the talk, I will probably talk about this paper with Dongmin Kang and Spencer Stubbs. Spencer is my student. And probably in the second half of the talk, I will try uh, to 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 talk about these two papers that I wrote with Andrea Ferrari, Nick Gunner, and Thomas Krutz. In this talk, I'm going to discuss, as Joanna briefly introduced in her talk yesterday, I'm going to talk about the 3D n equals to 4 theories that are defined on a half space. So we have n equals to 4 theory defined on a half space. We say R minus times some 2D space C. And the being a 3D n equals to 4 theory, we can do two different full topological twists. This is sometimes called A twist and B twist. This is, I think, what corresponds to what Joanna talked about. This is sometimes called an H twist, and this is sometimes called an C twist. And as a result, we obtain two different topological field theory from one 3D n equals to 4 theory, and I will call them TFT-A and TFT-B. Okay. So in general, these 3D topological field theories have many local operators, and that local operators comes from, of course, the local operators of original theory. This original theory has a lot of local operators, and some of them survives under the cohomology of, for example, in this case, you pass the cohomology with respect to the Coulomb supercharge QA, and then in this case, you pass to the cohomology with the Higgs branch supercharge QB. And then the operator that survives cohomologies are in TFT-A, it's a Coulomb branch operator, and TFT-B is an Higgs branch operators. Higgs branch operators. Okay. And the main question that I would be interested in today is which class of 3D n equals to 4 theory supports a rational the boundary vertex operator algebra on the boundary. Which class of 3D n equals to 4 theory admits some boundary condition that supports some rational vertex operator algebra for both twists. How do we answer this question? In general, if you pick some random 3D n equals to 4 theory, generically, the VOA that you obtain on the boundary are non-rational, and in fact, they are, in general, logarithmic vertex operator algebras. And the reason, the main reason that you obtain some non-rational VOA on the boundary is mainly due to the existence of the local operators of this TFT-A and TFT-B. Okay. So first of all, the rationality of VOA implies the semi-simplicity of the category of line operators on the Berg TFTs. And you can also argue that if the category of the line operator is semi-simple, then that topological field theory doesn't have any non-trivial local operators. So the first necessary question that we should impose in order to obtain some rational VOA on the boundary is that for TFT-A, you'd like to impose that there's no Coulomb branch, the zero dimensionality of the Coulomb branch. So you'd like to impose the dimension of the XC. XC is a Coulomb branch of this original theory, is 0. And also, in the case of TFT-B, you'd like to impose that dimension of the Higgs branch is 0. Okay. So, but this is one necessary condition, but it's not sufficient. And another uh, very important necessary condition comes from the other branch of the each theory. So, for example, let's just focus on a TFTA first, because this is just you can just swap the Higgs and Coulomb for just this discussion. So if you think about the TFTA, so if you first think about the 4D n equals to 2 version of the VOA correspondence, there is a Higgs branch conjecture of Beam and Lastelli that tells us that the Higgs branch corresponds to what's called the associated variety of that vertex operator algebra. And there are similar statements for the topological TFTA for the 3D n equals to 4 theories. And based on lots of examples, Beam and Ferrari recently actually argued that the VOA that corresponds to the TFTA has an associated variety, which is actually the Higgs branch of the original theory. Okay, and what we can also what we know on top of that is that the rationality of VOA also implies what's called the leastness of the corresponding VOA, and that actually implies that the dimension of the associated variety is 0. Okay, so another necessary condition is that for TFTA, on top of this condition, you also need the condition that the dimension of the Higgs branch is also 0. Okay, and the same is expected to be true for the TFTB. So in this case, its associated variety is expected to be a Coulomb branch. In this case, you'd require that this is go to 0 as well. Okay. Of course, the precise mathematical relation between the condition when the 3D n equals to 4 theory has a rational VOA and this particular condition that I mentioned is something that needs to be more carefully investigated. But this discussion at least tells us that we should look at those theories in order to find some 3D n equals 4 theory that supports a rational VOA. Okay. So these theories are called the rank 0 theories. The rank 0. I'm going to focus on the CFT, so rank 0 SCFTs. So by definition, this is a theory so that the dimension of the Higgs branch and the dimension of the Coulomb branch are both 0. Okay. We believe that it's sufficient, but it's mainly based on examples, and we really don't know yet. Sorry? The vacuum of which theory? The vacuum of the original SCFT. This is an SCFT. It's an SCFT. So 3D n equals 4 theory is an SCFT. Mm-hmm. 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 Yeah, those are usually the TFT with semi-simple TFT is a theory, the topological field theory that doesn't have a local. But in general, the topological field theory can have a local operators, and that's actually an important source of those logarithmic VOAs that you can often find in generic 3D n equals to 4 theory. Yeah, that's correct. Mm-hmm. Sorry? Say again? Some line? Uh-huh. Sorry, on the cycle, the operators on the cycle, what? Yes. Yeah, sure. Sorry, say again. Oh, the mixed branch. Well, of course. Well, in principle, there could. I don't know. I think it's a good question. Yeah, but I don't know the good answer for that. So the rank zero theories. Um, so the problem is that the rank zero theories are difficult to construct. So, for example, in 4D n equals to 2 theories, we believe that there doesn't exist any such a thing. The 4D and higher dimension, we believe the smallest rank that one can have, rank in higher dimension is defined as like a minimum of the dimension of the Higgs branch and Coulomb branch. And we believe that there does not exist anything like that in 4D n equals to 2 theories. In 3D n equals to 4 theories, we also believe that there does not exist any Lagrangian interacting 3D n equals to 4 rank 0 SCFTs. Okay? So we believe that abelian theories with BF terms. Three. Uh, uh, yeah, probably flows down to trivial theory, I guess. Trivial TFTs. Yeah, it does. I think it flows to some non-interacting theories. Yeah. So it's difficult to construct the interacting Lagrangian rank 0 3D n equals to 4 theory. And in fact, in 3D n equals to 4, but there exists an example, and those examples, and some scattered example exists, and one of the first example was found by Masahito and Dongmin Gang. This is called the T minimum theory. And in fact, the theory doesn't have an n equals to 4 description. It only has an n equals to 2 Lagrangian. And n equals to Lagrangian is very simple. So U1 gauge theory with Chern-Simons level 3 hop coupled to one single chiral multiply. And you can argue by some other indirect checks that this actually flows in the IR to a rank 0 theory. That has an n equals to 4 symmetry, n equals 4 enhanced ones. And the rank 0. Okay. And there are all other scattered examples where you have to, so this part is actually something that it's difficult to predict in first principle from the n equals to Lagrangian description. So you have to rely on some accidental enhancement, and also there are also some other mechanism if the theory involves like something like a T of SUN type theories. But there are not many examples that you can systematically construct. So the reason that this theory is called T minimum theory is that this theory is also believed to be the minimal SCFT in 3D n equals to 4. So for example, if you compute the central charge of this theory, is the smallest among the known examples. And also, it's also you can derive that this theory can be something obtained from the dimensional reduction of the 4D the minimum address Douglas theory, which is sometimes called this A1, A2 type theory. So, so these are there are these examples and some of the T of SUN. You start from the T of SUN theory and then gauge some of the flavor symmetries to get the rank 0 and an enhancement of the supersymmetry at the same time. So those are the known examples so far. And you can compute a lot of observables of this theory because it has an n equals to 2 description. You can compute lots of bulk observables like various supersymmetric quantities. And in fact, we expected that this theory would support some rational vertex operator algebra on a boundary. And in fact, the bulk theory suggests that for both TFT-A of T-min and TFT-B of T-min, from the bulk computation, you can actually extract all the modular data of that rational vertex operator algebra. And the bulk computation seems to suggest that these two theory actually has a modular data that is compatible with the Liang model. The simplest non-unitary rational VOA, which is sometimes called the Virasoro minimal model M2,5. Okay. This lives on the boundary of the theory with some boundary condition.
Is it some kind of a universal boundary condition, or do you have to fix something else?
We have to fix some. We have to fix the boundary condition among many.
Different boundary conditions.
We can have different boundary conditions for one TFT. Yeah.
So you say that you can pick a particular one which gives rise to.
Yeah. For this statement, I haven't fixed any boundary condition yet. What I just mentioned is that from the bulk computation without any boundary conditions, what you can fix is a modular data of the VOA on the boundary that lives on the boundary, and that modular data is compatible with the modular data of the Liang model. I'm going to, in the second part of the talk, I will try to tell you which boundary condition do we have to impose to obtain something like that. Okay. Sorry, say again. Yes, yeah, up to orientation issue that I'm going to illustrate momentarily. Yeah, but from the bulk data, you cannot fix all the modular data. You have an access to a part of the modular data. Yeah, that part is something that's shared by all the boundary VOAs. Other questions? Uh-huh.
Current knowledge that bulk doesn't have access to all the modular data, or is it obvious that it will never have?
Sorry. Sorry.
Do you think in 10 years, bulk method will access more modular data?
Well, what I meant is that you can compute the partition functions on cipher spaces of this TFT-A and TFT-B, and there are particular modular data needed to construct the partition function on the cipher spaces. So it's some particular components of the S and T matrices that we can extract from the partition function computation. Uh-huh. Yeah, but not exactly the same. But also the bulk data, yeah, up to some substitutes I'm going to mention. Other questions? Okay, so the plan for today's talk is the following. So I mentioned that the construction of the rank 0 theories relied on some accidental phenomena, like the accidental supersymmetry enhancement. So the natural question here is that, is there any way to more systematically construct those rank 0 theories, systematic? And the answer is yes, in some sense. And as a result, we will try to, I'm going to define a class of theory, the T and K, the labeled by, this is a 3D n equals to 4 rank 0 theories, which are labeled by two positive integers, n and k. And then the simplest member of this theory, the t1, comma 1, would be identified with t min. Okay. And then probably more important question is, can we identify their boundary algebras? Okay. And we will see that for TFT A and K, in A-twisted theory, the boundary algebra is going to be a simple affine Lie algebra of OSP 1/2n level K. And for TFT B, that corresponds to T and K theory, is going to be the minimal W algebra level K of SP to n. Okay, and these two theories are in fact important class of the rational VOAs. Okay, and we will be able to construct some of them very explicitly at the level of the operator product expander. Okay, that's what I was going to say. The number 3. So the 3D n equals to 4 theory has a mirror symmetry, which is a statement that there exists a pair of 3D n equals to 4 theory, so that the Higgs branch and Coulomb branches are exchanges. So in our setup, it exchanges TFT A of T1 with the TFT B of T2. Okay, and we will in fact argue. Actually, I'm not going to argue. We have some evidence, a very strong evidence that tells us that T and K theory is actually mirror to T of Kn, swapping K and N, and taking the orientation reversal. Okay, so these are 3D n equals to 4 mirror. And this mirror symmetry is going to tell us, it's going to tell us something about this boundary algebra. It's going to tell us that there exists a new class of level rank dualities. Yeah, I will try to explain the precise meaning of the level rank duality probably toward the end of the talk. Among these two classes of theories with exchange of the K and N. Okay, so in particular, we will see that. So for example, when K equals to 1 here, the L1 of OSP 1/2n is going to be level rank dual. It's precisely the same level rank duality that we are familiar with, the level rank duality between this SL and K affine Lie algebra and GL, K, and Lie algebra. So it's exactly the same thing. So in the left-hand side, we have L1 of OSP 1/2n. And in the other side, we swap the K and A, and we set K equals to 1, so it's SP2. And this is exactly then the Virasoro minimal model of M2, 2, N plus 3. So there is an Virasoro minimal model M2, 2, N plus 3. Mm-hmm. Right. Mm-hmm. Yeah, this theory, a large class of those theories can be derived from the 4D Algebras theory. It's actually in work in progress at the moment. Yeah, probably, but I won't say more about the 4D connection today. Any other question? Yes, yes. Right, right. It's different from this. Yeah, a subset of those Algebras theory labeled by G and G prime appears as a reduction of this, but it's not related to this. It's going to be also related. Interesting. This is also going to be labeled by two Dinkin diagram. So it's tempting but it's not. It's actually a bit complicated. Okay, So these are the plan. Yes, but I'm going to focus on 3D n equals to 4 theory, whose Coulomb branch and Higgs branch are both just points. Yeah. Mm-hmm. I think it's a good question. I don't know the answer. Yeah. Yeah, but it. Yeah, I don't know the answer. Yeah. Huh? Uh-huh. I'll talk about that soon. Other questions? So I will first present the description for this theory, T and K, and then I will tell you where did that come from, okay? So class of rank zero theories. So as I mentioned, all we can hope for is n equals to 2 description of this series, and we can hope that some of them will flows to this really n equals to 4 rank 0 theories in the IR. So this class of theory that I'm going to introduce also has a U1 description. So it has U1 to the n theory. It's an abelian, the abelian Chern-Simons meta theory that has a Chern-Simons level matrix K. It also has n chiral multiplet phi, and the phi is charged under U1, the exactly one phi is charged under exactly one U1. Okay, so it's just it's a very simple abelian Chern-Simons meta theory. It's actually n equals to 2. Okay, and we take K to be the following matrix. It's just Cartan matrix of it, but here A and B are one of the following the Dinkin diagrams. It's an A type, D type, E type, or T type. So T type is what's called the Tadpole diagram. So TR, you can think of it as you start from the A of 2R and fold it in half. Okay, this is called Tadpole. And then you consider the Cartan matrix, C of A is a Cartan matrix of any of these choice times C of B and inverse, and this is the usual Kronecker product. Okay, so for example, the C of T R is going to be, it's the same as the AR Cartan matrix, something like this. But the very last entry, which is 2 for AR, is just replaced by 1. Every other component is the same as an AR. Okay. And my claim is that this theory, with the suitable superpotential deformation, all flows to the rank 0 SCFTs, okay, with some superpotential deformation. The superpotential deformation is needed because if you look at the n equals to 2 description of this theory, it has n U1 copies, so it's gonna have the n topological symmetry, n U1 topological symmetry, and we want to lift all of them. We don't want any flavor symmetry left in the IR theory. So in order to lift all of them, we add some superpotential, And you will see that there exactly exists n-1 terms that you can add in the superpotential so that it exactly breaks the all but one, the U1 flavor symmetry. And that U1 remaining flavor symmetry is going to be the part of the R symmetries in the IR 3D n equals to 4 theory. So we are going to focus on the case where the TK is, sorry, the case where the B here is TK and A is A1 actually. This A1, which is just 2. Okay, so this T of NK is defined by this, where the B is TK and A is A2 and plus 1. So it's a bit different from the class that I'm describing. Yeah, it's a generalization of the class that I'm going to describe. So it's for simplicity, I will just take n2 0, n2. So I think it's 2n plus 2n minus 1. Yeah, so that t1 comma 1 is yeah. So but I will just focus on this just for simplicity today. But probably you can ask the question. I don't have a full answer yet, but probably the reason that I took that particular ADET is going to be clear when I actually mention how I came up with this class of theories. Okay. Huh? Sorry.
How does this K enter?
K is a Chern-Simons level, the matrix. These are the UV effective Chern-Simons level. Yeah. So for so including that. Yeah. So for example, that T min corresponds to the case where you have T1, A1. So you see that T1 is just 1, and then A1 is just 2. So that effective level is 2, right? So it's, yeah. No, it's completely different. No, sorry, it's completely different. So for this choice, there you can show that there exists exactly R-1 monopole operators that you can have BPS monopole operator, which are gauge invariant, so that you can add to the superpotential. So these are the VM1. Hypertoric. Why? Yeah, I think when you have more, and n is larger than something like hypertoric seems to exist when you have different, yeah. Yeah. Point. Yeah. I think it's just 1 point. Just 1 point. I think so. Yes. Yes. Well, I don't have a description, that precise description at the moment for each class of theories. I think it's on, yeah. Um, um, maybe it may be possible, but it's just not on top of my head at the moment. Yeah. So there are R minus 1, sorry, was there any? Okay. So there are K minus 1, not K. Yeah, so there are too many K, so there's small K. So this is a small K. So K minus 1 monopole operators, and these monopole operators have charges. Those M's are M1, from M1 to Mk minus 1s are exactly the first K minus 1 rows of the AR Dinkin diagram. So it's also it also has a very simple description, and you can show that these are all gauge invariant half VPS, and it exactly breaks the U1 K. So in this case, this N is the small K. So you had U1 to the K topological symmetry for each of the gauge group, and this breaks down to the U1. And I will call this the U1 axial symmetry because this is going to be identified with so in the UV theory, we have the U1R times this U1A, and in the IR, we expect this to enhance to the full R symmetry group, the SU2H times SU2C. Okay. So we took this, the N is a dimension of this matrix. And if I take this 2 and then TK is number 2 and TK, it's going to be the N is equal to the small k. So I have the U1 to the K theory with this symmetry. It's expected to enhance to this in the IR. Uh-huh. Well, you can also try to draw some keywords for, well, we can try to draw a keyword for each node corresponds to U1 factors, and well, any arrows corresponds to like a linking between the Chern-Simons, linking that corresponds to Chern-Simons level. You can do that, but yeah. The K equals to 1 and N equals to 1. Well, it's just a node. This is node, one node thing. Well, when you have different N's, for example, you can have many like nodes for given U1s, and then Chern-Simons level can be thought of as an arrows between those. Maybe these are like these arrows can be thought of as what's described by this matrix. Yeah, so you can think of it as a Kuiper gauge theory, but I just don't know what we can learn from by doing that. Yeah, it's not the usual Kuiper. Yeah, yeah, yeah. It's not the usual Kuiper. Yeah, yeah. No. So of course, we cannot prove that this theory all flows to the n equals to 4 theory, but there are many indirect evidence that this indeed flows to the n equals to 4 theory. So for example, if you calculate the superconformal index of all this theory, because you have a n equals to 2 description, the superconformal index I, it starts from 1 minus q minus eta plus 1 over eta. The eta is a fugacity for this guy, u1x here, and then q to the 3 half. Okay, so these part varies as you vary the theory, but this part is universal for everything. And this particular term signals the existence of extra supercurrent multiplet that sits in n equals to 4 part. So it's the first signal that in the IR we have. Of course, this is not a sufficient condition or necessary condition. The existence of this term actually doesn't, but yeah. No, it's just a superconformal index. It's a yeah. At the moment, I'm just doing the thing on the S2 times S1 as usual. Other questions? So this term is the first signal that we are going to have something like n equals 4 in the IR. And also, you can take the limit of those fugacities so that it computes it counts the Coulomb branch chiral rings and the Higgs branch chiral rings. And this is computed by the Coulomb branch index and the Higgs branch limit of the index, and you can check that these are both 1, which means that the only thing exists is an identity operator there. Right? And it matches with the fact that we don't have any like, non-trivial part. Well, the Coulomb branch, it's very difficult to say what is the Coulomb branch and what is the Higgs branch because those are just points. But here, well, I can define, these are just points, so it's really doesn't mean much too. Yeah, I'm using the n equals to 2 Lagrangian description of the theory. Yeah, this is not well defined in n equals to 2. Using the SU2H and SU2 acts on specific way on the Coulomb branch operator and the X branch operator. So it has some specific charges under this U1R and U1A. So that's what I'm referring to. Okay. Yeah. Uh-huh. So yeah. We don't have a Coulomb branch. They are all lifted up. Yeah. We have a Chern-Simons level, right? That's important. Mm. 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 Mm-hmm. Yeah. I will move on. Yeah, that's important in enhancement, showing the enhancements. Yeah, yeah. Yes. So there are some, you are asking the quarter VPS monopole operator that sits in the extra current multiplet. Yeah, that we know what they are. Yeah, they actually play an important role later because we are going to we want to do some topological twist of the theory, and it's in general difficult to do the topological twist when we don't have a Lagrangian description, and that monopole operator will actually plays an important role when we do this analysis. So the maybe I should say where did I come from? How did I come up with this theories? Huh? You can calculate the superconfirmation index of I that counts local operators of the theory. You using the n equals to 2 Lagrangian description. This Lagrangian description is a Lagrangian description that are defined on a high energy. And right. No, you can just compute it for a given Lagrangian, and that information is invariant under the RG flow. Yeah, so yeah. So where did that come from? So it actually came from the characters of this series, the characters of the rational vertex operator algebras. Huh? What do you mean? Uh-huh. Uh-huh. Okay. Yeah, that I don't, yeah. It doesn't, yeah. Yeah, okay, that might be, okay. Yeah. So the important property that we use is that the rational VOA, the characters of the rational VOAs are modular functions. So And it's known that a large class of the characters of the rational vertex operator algebra can be written in one of the following forms. So the characters, the chi, of the Q of the rational VOA, in many cases, it has a following expression, what's called the fermionic sum formula, and then M is a non-negative integer to the maybe N there, and then find the Q to the N, M, sorry, K, N, N, plus B, N, plus C, and there is the N copies of Q per comma symbols. Okay? In many characters of the rational VOA takes this form. Sorry, yes, sorry. That's the starting point. Yes, yes, yes. So you can ask the following questions. For which, so here K is the n by n matrix, then B is the dimension n vector, and C is some rational number, right, for the rational. Then many the characters, many RCFT characters take this form. So we can ask for which triple K, B, C, this chi Q is actually a modular function under some under some congruent subgroup of SL2Z, so that it can be a candidate of an RCFT character. Okay, you can ask what kind of KBC this becomes a modular. Okay, so this question is actually asked by Don Zagier and Nam and Hovan in early 90s, and this question is still an open problem, but we have some classification. For example, when n is 1, 2, 3, it's almost fully classified, and there are actually not many examples where this becomes a modular. For example, n equals to 3, there are like 20-something many K matrix that makes this modular with some infinite families that we can track. And I will mention that soon. So, and also important class of the theories where this chi is a modular is precisely the case where this matrix K takes that form. Okay, so that's the reason, this is a motivation to come up with this theory. So that when, in many cases, K takes the form of the Cartan matrices of this. Okay. And as Pietro mentioned, that this is actually the half index of those theories. The form of this can be thought of as the partition functions of those theories. Maybe I will call this theory TAB of TAB, when this K is this matrix on the 2 times S1 with the twist Q. Okay. Mm-hmm. Uh-huh. Okay. Mm-hmm. Okay. Interesting. So is it exactly the same Chern-Simons matrix? Okay, maybe I can ask him about that. Yeah. Uh-huh. Yeah, now we need to talk about the boundary conditions. So this partition function appears when we impose a Dirichlet, some particular Dirichlet boundary conditions to everything, every multiplets that we have in the theory. So of course, it's natural to ask. There are some classifications we can ask. Do those theory all flow to rank 0 theory? And the answer is almost yes. There are some examples where it actually flows directly to the TFT, and then we obtain some unitary TFT in the IR. And all the other cases, it seems that it flows to the rank 0 theory. Okay. this theory. So I'm talking about this theory now. So we start from this theory and to flow to the IR.
The reason I'm confused is what 10 minutes ago you said we don't know what those two hypotheses are. Now you say that we proceeded.
No, it's all conjecture. We don't we actually know that whether it actually flows to n equals 4. We have a lot of, yeah, maybe I should say that we have a lot of evidences that all of these theories flows to the n equals to 4. And for this example that I erased here, this example when A is just A1 and then B is T K, this character is precisely the character of the Virasoro minimal model. So for that example that I will call T sub K, TFTA, if you look at the TFTA, you can also insert the Wilson loop operator to obtain the characters for non-vacuum modules. And you can actually find that this half index of the A-twist theory is precisely the character of M2, 2K plus 3, the alpha. And alpha is labeled by the insertion of certain Wilson, some simple Wilson loops of the theory. And this strongly suggests that if you impose a Dirichlet boundary condition, it's actually Dirichlet, exceptional Dirichlet and Dirichlet. So at the end, you see, Dirichlet for the vector multiplet and exceptional Dirichlet means that we set this to some non-trivial number C, which is non-zero. Okay. So when we do that, it reduces the Virasoro minimum characters. And for TFTB, W alpha is some choice of Wilson loop that we expect to correspond to the simple lines in the IR. So TFTB, we obtain the same set of characters, but the order are all reversed, so that we have -1 to the alpha, and then chi of M to K plus 3, but now this order is reversed like this, okay? So our original question was, what is this? What is this algebra? It's like a vacuum character is, vacuum character, vacuum character corresponds to some non-vacuum character of the Virasoro minimal model. So we wanted to identify this algebra. This is expected to be Virasoro minimal model. This is something that must be something that's closely related to Virasoro minimal model. So what are the precise relation? And can we actually compute the OPEs of the boundary operators? Okay. Uh-huh. Mm-hmm. Yes, yeah. Mm-hmm. Uh-huh. There exists something like that. And there are also interesting theories. Yes, yeah. So we want to calculate the explicit OP. So far these are all indirect evidences. So we want to calculate something more explicit. Maybe we can just focus on TFT, and we will just focus on the simplest possible case, the T-min with the TFTB, okay? So that where you obtain the Virasoro minimal model, but the order is swapped, the two characters are swapped case. What's the algebra? But just to calculate, before we calculate the algebra, there was an important obstruction, which is the fact that we don't have an n equals to 4 Lagrangian description. In general, it's very difficult to analyze topological twisting of a non-Lagrangian theory. But we can do that in two-step, what's called the two-step twisting procedure. The strategy is to use the two-step twist. So I will talk about the T1,1 and the B twist. So the strategy is to first go to the holomorphic topological twist because we have an n equals to 2 description. It admits an HT twist, and we can calculate a perturbative OPE in that HT twisted theory. And then there is a systematic way to deform the HT twist to the full topological A or B twist, and that will have some effect in action of original action of the theory. And then we can analyze a correction of our OPEs, which is the effect of that, the deformation from the HT to the full topological twist. And finally, we can incorporate some non-perturbative. Okay, so that's the strategy. So the perturbative OPE in the HT twist. I think my time is almost up, so maybe I'll just briefly mention the strategy and then, yeah, do you have a question? Yes, holomorphic topological. So it's a holomorphic. No, this is a holomorphic in this direction, and it's a topological in this direction. No, but there are operators that cannot escape to the bulk. So for example, if you think about this QA or QB phi equals to psi algebra, and if you impose a boundary condition, say that psi equals to 0, and phi is in a cohomology only at the boundary, so it cannot escape to the boundary. So those phi are something that can form a non-trivial OPs among themselves. The H2 twist is at the level of UV. So to calculate the perturbative OP, you just see which operator survives on the boundary, which operator can form trivial OPs among them, and then you under that boundary condition, you can check that there is a current, the U1 current JZ, which is level 2, which is from the effective level 2 thing, and then there is also a fermions lambda. Lambda z in the chiral multiplet. That was a fermion that survives in the boundary condition that originally was a part of the chiral multiplet fermions. Okay, and you can calculate the perturbative OP. These are the simple OP because we know what the OP is among the current. The JJ is just a 2 over z minus w squared, so you know how it is. So we can calculate the perturbative OP. And then you can deform it to the an A or B twist. First of all, you change the twisted spin, and you now work with the twisted spin with respect to A and B twist. And then you deform the differential. And I don't have time to say too much about how that deformation works, but there is a very systematic way that allows us to deform the differential. And the effect of the deformation of the differential is actually add a superpotential term in the HT twisted theory. And that superpotential term is exactly that monopole operator that Stefano was asking, the one that was important to show the supersymmetry enhancement. So you can do that, and then finally you do the non-perturbative completion. But non-perturbative completion is also come in the form of the boundary monopole operators, and that there is JG, and there is a boundary monopole operator V plus and V minus, and they together form the SL2 at level 1 algebra. So it started out from the U1 at level 2. It's a usual story that the U1 at level 2 at some radius, square root of 2, enhances to SL2, 1. And the vertex operator that usually corresponds to the vertex operator in the U1 algebra is precisely the monopole operators that are in the boundary operators. Okay. And this lambda is going to also form a doublet under this SL2. So we have 5 generators, these 3 bosonic generators, and 2 fermions, which is lambda is the highest one of them. So we have 3 bosonic generators, 2 fermionic generators, and you can see that by working out the algebra, these are affine, the simple affine OSP 1/2 at level 1 algebra. Okay, it's a very simple non-unitary VOA that has a central charge 2 over 5. Okay. Sorry? Yeah, it's a minima case, T-min case. Right. Right, but this is a B twist, so it's not something that we obtain from the direct dimensional reduction. So what we obtain from the direct dimensional reduction is an A twist, because that's what C is a Coulomb branch of the original theory. So in that case, we see the M2,5, which is an expected VOA for the A2 theory. So maybe I will say some comments about the level rank duality before I finish. So we expected something like Heeyeon at the first place, and we obtained the L1 OSB1/2, and it's actually closely related to the M2,5. So the picture is the following. So far we have been looking at the right boundary condition. So this theory is not invariant under parity, because maybe you can infer from the fact that the theory has a Chern-Simons level. This is invariant under, it distinguishes left and right boundary. So far we have been talking about the right boundary condition, and we haven't actually seen that the TB of T minimum theory supports L1 of OSB 1/2. And you can also ask what exists on the left boundary condition. So in the left boundary condition, the Dirichlet boundary condition is sick. If you calculate something on there, everything is going to diverge. It's not going to make sense. But on the left boundary, there also exists some equally good boundary condition, which is to impose the Neumann boundary conditions to everything. So you impose Neumann, but this Neumann boundary condition has a gauge anomaly. And to cancel that, you need to add 4 fermions. Okay, and if you calculate the character of this combined theory, you exactly obtain the M2,5, the expected Virasoro minimum model. So if you think about this picture is actually very similar to the usual level rank story. So you have in the Berg, you have the usual level length, or you have the Chern-Simons theory, ordinary Chern-Simons theory SUN at level K. And then on the right boundary, you can impose the Dirichlet boundary condition, and you can argue that there is an as a U at level K, N at level K. And then here you this is under the Dirichlet boundary condition. In the left boundary condition, you can also imply the Neumann boundary condition. But again, this is an anomalous boundary condition. You have to add the n times k fermions to cancel this boundary anomalies. And the result is that the total result that you can obtain on the left boundary of the theory is the following picture. So you have the nk fermion algebra. And inside of nk fermion algebra, there sits SUN K algebra. And in fact, the coset of these two is precisely the UK at level n. And in fact, these two form a mutual coset inside the nk free fermion. And from the fact that the nk fermion has a trivial category of module, we can actually infer that these two are the dual to each other. So you can think of it as the category of modules of each boundary condition is equivalent to the category of modules of the line operators. And you can think about like a line operator stretched between these. And this induces module on the both end side. So if they share the Berg boundary, and this Berg theory has a trivial category of line operator, you can argue that these two theories have a same category of modules up to the reversal operating. So exactly the same situation happens here as well. So you can have like a line operator that are stretched among between these two boundaries, which induces the same category of module on the other side up to the reversal operating. So this is, we can actually do this game for the entire class that I mentioned, and that's how we get the level rank duality between this OSB 1/2n at level K and the minimal W algebra at the level that I mentioned. And at the same time, the level rank duality is also the mirror symmetry. You can check by various index calculation that they are actually different to each other up to the reversal of the orientation. Okay, yeah, I will stop here. Mhm. Uh-huh. Mhm. Sorry, say again. The B twist what? Uh-huh. That's A. Yeah. Um. Why? Yeah, but the cigar compact you can obtain what you can obtain by the cigar compactification with this twist reduction, the turning on the twisted flux. Yeah, yeah, yeah.
See this picture as being one boundary is at the tip of the cigar and the other end is the end.
No, I think the maybe one end of the cigar you obtain. I think the boundary condition at the tip, this tip of cigar, is going to be the Neumann boundary condition with some left, probably something like a left. But you obtain actually something different from that. It's not the Neumann plus 4 fermions. It's something else. Yeah. Yeah, maybe you don't obtain that directly on the nose. It's still work in progress, so we don't have a full picture yet. But it looks like the tip of cigar you have. It's also some boundary conditions of the U1 3/2 is 1 chiral, but with something is slightly different. It's actually Neumann. Sorry, it's a Neumann boundary condition to everything, but I think you don't have a Fermi multiplier, but something else. Yeah, so something else is obtained. Yeah, it would be nice to directly obtain this picture from the 4D reduction. Something very related is directly obtained. Yeah, I think that's yeah as much as I can say at the moment. We can do the calculation of the strongly coupled SCFT that we cannot calculate anything, but we have a UV description that allows us to calculate something. Well, we can derive, for example, this new level rank duality from this picture, right? Otherwise, Mhm. No, we computed in UV and we used the property of the UV calculation that this is invariant on our IR. I calculated the, yeah.
Only step one happens. Only step one happens before flowing. You're saying?
Flowing, well, after this step, you can also think of it as like a computation is all done at the level of the UV, and then you go down to you use the property that those holomorphic properties of those theories are preserved under the RG flow. So it's the same in the UV and the IR. Mhm. Um, what do you mean? Where do I use the fact that I flow to the IR? Well, the IR theory has it. Yeah. Yeah, the fact that we have an n equal 4 that exists only in the IR. So the deformation to the A and B twist is a deformation at the level of n equals 2. We can interpret that as an actual topological twist when we went down to the IR. So those steps are all something that we can do in the UB. And for example, the step 2 is at the level of just n equals 2 theory. This is just a deformation of the theory, but we can interpret all the yeah.
why is it important to do this?
Well, otherwise, we want to obtain some topological theory on the 3D on the IR. So otherwise, we cannot do a topological twist in the n equals to 2. I wanted to obtain the topological field theory. Yeah.
So for any statement you made
Mhm.
about the conformal field theory
Mhm.
before
Mhm.
joining
Mhm.
that this what you're saying is what you're saying is that this last picture
Uh-huh.
happens in the last picture happens in
Yeah. 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 Uh-huh. Uh-huh.
That's like a show wide geometry, and then Thomas and others discuss some more examples of that in the context of that.
Right. Right.
So, and then this is a one subclass of that. So that brings into the question of if you start with more general, like here and stuff.
So yeah, so which class of the level, more general level rank duality are you talking about? It's like a non-rational. It's for the non-rational theory that you mentioned. You mentioned some not. Yeah, yeah, it's a rational version of those stories. I think you can think of it as a. Yeah. There was no example of the rational level rank duality other than the Chern-Simons theory. Yeah.
So in a sense, you exhausted all those cases.
I'm not sure if it exhausted every rational theories, but I don't think we exhausted everything. There are certainly more examples. Yeah.
It might be interesting to try to move upwards.
The backward to where?
From the discussion of
Uh-huh. Uh-huh.